The study of corrosion inhibition ability of hexamine on mild steel in acetic acid solution. The ability of hexamethylene tetraamine, hexamine, as corrosion inhibitors for mild steel in 0.5, 1.0, 1.5, and 2.0 m acetic acid solution have been studied by polarization, impedance, weight loss and scanning electron microscopic measurements, which confirm the inhibitive action of hexamine. The studies were carried out at room temperature as well at different temperature range of 303 to 333 K. The inhibition efficiency of hexamine increases with increase of inhibitor concentration. Thermodynamic parameters governing the adsorption process like activation energy, standard free energy of adsorption, standard enthalpy of adsorption and standard entropy of adsorption have been calculated and discussed. The adsorption of hexamine is found to obey Langmuir adsorption isotherm. The study suggests that hexamine acts as a mixed-type inhibitor, predominantly cathodic in nature. Changes in impedance parameters were indicative of the adsorption of hexamine on the mild steel surface. The SEM photographs show a clearly different surface morphology in the presence of inhibitor. The results obtained by electrochemical measurements are consistent with the results of the weight loss measurements. The results obtained show that hexamine acts as an effective corrosion inhibitor for mild steel in acetic acid and inhibition efficiency reaches up to 87.25% at a very low inhibitor concentration of 15 mm. Keywords: corrosion, inhibitor, mild steel, hexamine, acetic acid. Introduction. Metals and alloys are the backbones of the engineering field. Industries are heavily depending on the use of metals. The metal and alloy structures can be damaged by corrosion. Corrosion of metals draws the greatest amount of attention for safety, environment, and economic reasons. 1. Since metal have a high electric conductivity, their corrosion is usually of an electrochemical in nature. Due to good mechanical properties and low cost, mild steel is an important material in many industries. It is widely used as construction material for chemical reactors, heat exchanger and boiler systems, storage tanks, and oil and gas transport pipelines. 2. 3. But it is suffering from certain type of corrosion in acidic and alkaline media. 4. 5. Acetic acid is one of the reactants in the manufacturing of cellulose acetate, plastic, acetic anhydride, and in textile processing. However, acetic acid is weak acid, but it provides sufficient amount of protons to act as true acids towards most metals. Several approaches have been proposed to protect the metal from corrosion. The use of inhibitor is one of the most practical method for protection of metal against corrosion in acidic media. 6. Most of the organic compounds having heteroatoms such as N, O, S, P in their aromatic ring or long carbon chain and having P electrons were reported as the efficient corrosion inhibitors under aggressive environments. 7, 8, 9. Hexamine was reported as effective corrosion inhibitor for different metal in various acids. 10, 11, 12. In the present work, the efficiency of hexamine as corrosion inhibitor for mild steel, MS, in acetic acid media is studied by weight loss and electrochemical methods. 2. Experimental. A. Preparation of sample and solution. The test specimens of size 4.5 times 2.0 times 0.2 cm having an effective area of 0.2097 dm2 were prepared from MS having chemical composition of C equals 0.25%, Mn equals 0.5%, Si equals 0.35%, P equals 0.09%, S equals 0.07% and Fe equals 98.74%. The test specimens were cleaned by washing with distilled water, degreased by acetone and again washed with double distilled water, finally dried and weighted by using electronic balance. Aqueous solution of acetic acid having concentration of 0.5, 1.0, 1.5, and 2.0 m was used as corrosive media, prepared by diluting acetic acid of analytical grade in double distilled water. B. Weight loss measurement. For weight loss measurement, the MS specimens were each completely suspended in 230 ml of 0.5, 1.0, 1.5, and 2.0 m acetic acid solution in beaker of volume 250 ml, with and without hexamine as inhibitor having concentration of 1, 5, 10, and 15 mm at room temperature of 303 K, for 24 hour. C. Surface cleaning of test specimens. After exposure period, to remove the rust from MS test specimens were cleaned by Clark's solution 13, 14, followed by distilled water and after that washed with acetone and then dried with air dryer. From the weight loss data, corrosion rate, CR, was calculated. D. Temperature effect. To study the effect of temperature on corrosion of MS, the test specimens were completely immersed in 230 ml of 1.0 m acetic acid solution without and with different concentrations of hexamine at 313, 323 and 333 K for 2 hours. After exposure period, the test specimens were weighed to determine corrosion rate. From the weight loss data, inhibition efficiency, i.e., energy of activation, EA, heat of adsorption, CADS, free energy of adsorption, G degree ads, enthalpy of adsorption, H degree ads, and entropy of adsorption, S degree ads, were calculated. Electrochemical measurements. To study the mechanism of inhibition action and efficiency of hexamine on MS in acetic acid solution, polarization study, and electrochemical impedance spectroscopy, EIS, measurements had been carried out without and with 15 mm of inhibitor concentration. The volume of 0.5 m acetic acid as corrosive medium was kept 200 ml. The test specimen having area of 1 square centimeter was immersed in corrosive environment act as working electrode. A platinum electrode used as auxiliary electrode and saturated calomel electrode, SCE, as reference electrode. All the experiments were carried out at constant temperature of 298 K. Initially open circuit potential, OCP, was measured as a function of time, and after the stabilization of the electrode at OCP, the electrochemical measurements were carried out. The change in potential was measured by potentiostate, CH instrument model Chi 608C, made in USA. EIS was carried out in frequency range 1 to 100 kHz and AC amplitude of 5.0 MV. A graph was drawn by plotting real impedance, Z, versus imaginary impedance, Z. The typical Nyquist plots of MS was obtained in the absence and presence of the inhibitor in acetic acid solution. The value of charge transfer resistance, RCT, and double layer capacitance, CDL, were calculated. A comparison of EA values in the absence and presence of inhibitor indicates that the value of EA were higher in inhibited system than that of uninhibited system, Table 4. Higher values of EA in inhibited systems compared to the blank suggest a physical adsorption mechanism, attributed to an appreciable decrease in the adsorption of the inhibitor on the metal surface with increase in temperature 18-19, which is in agreement with other observation earlier published 20. According to whom for physical adsorption mechanism the EA value should be less than 100 kJ/mol1. The values of G degree ads were negative. The calculated negative value of G degree ads indicates the strong interaction of the inhibitor molecules 25 and spontaneous adsorption of the inhibitor on the metal surface 26. Generally, the magnitude of G degree ads around -20 kJ/mol1 or less negative can be assumed as due to an electrostatic interaction between the charged molecule of inhibitor and the charged metal surface, i.e. Fissorption, 27, 28. If the value of standard free energy of adsorption, G degree ads, is around -40 kJ/mol1 or more negative indicates a charge sharing or transferring from organic species to the metal surface to form a coordinate type of bond 22, 29, i.e. chemisorption. The mean values of G degree ads for the inhibitor was less negative than -40 kJ/mol1, indicating that the inhibitor physically adsorbed on the metal surface. The enthalpy of adsorption H degree ads was calculated according to the Van 't Hoff equation 3031, by plotting ln CADS versus 1/t with a slope of -H degree ads/RT. Van 't Hoff plot. The negative value of H degree ads suggests that the adsorption of inhibitors is an exothermic process 29-34, which reveals that inhibition efficiency of the inhibitor decreases with raising the temperature. The behavior can be interpreted on the basis that increasing temperature leads to the increase of the desorption amount of the adsorbed inhibitor molecule from the MS surface. The values of S degree ads were large and negative, that is accompanied with exothermic adsorption process. From Table 6, the negative values of S degree ads describes ordered phenomenon. This order may probably be explained by the possible formation of metal complex on the MS surface 35. D. Electrochemical measurement. Various electrochemical parameters such as corrosion potential, IJERT, corrosion current density, IJERT, and the value of Tafel parameters, SSA, SSC, SSB, derived from the potentiodynamic polarization measurements, were shown in Table 7. The percentage IE can be calculated by using the following equation 36, where IJERT U and IJERT I are the corrosion current density for uninhibited and inhibited system respectively. Values of IJERT decreases significantly in the presence of inhibitor. The value of IJERT for 0.5 m acetic acid is 244 cm2 in absence of inhibitors, while in presence of inhibitors the IJERT value decreased to 2.76 cm2, Table 7. Table 7. Polarization measurements of mild steel in absence and presence of hexamine in 0.5 m acetic acid. From the EIS spectra, the electrochemical behavior of the system is interpreted. High RCT value 18,643.10 ohm cm2 was observed in the presence of hexamine of 15 mm concentration, while the RCT value was 56.22 ohm cm2 for uninhibited acid. The CDL value decreases from 145.00 FCM2 to 0.0025 FCM2 in presence of hexamine, Table 8. This decrease in CDL value was due to the adsorption of inhibitor on the metal surface 41. These results suggest that the inhibitor acts by the formation of a protective layer on the surface, which modifies the metal/solution interface 40. The decrease in CDL values can be attributed to a decrease in local dielectric constant and or an increase in the thickness of the electric double layer, which leads to an increase in the IE. Therefore, it is suggested that the inhibitors act by adsorption at the MS surface or solution interface, and the change in CDL values is caused by the displacement of water molecule by the adsorption of organic molecules on the metal surface, thus decreasing the extent of the metal dissolution 42, 43. SEM images were used to investigate the surface morphology of MS before and after 24 hours of immersion in the -0.5 m acetic acid solution without and with inhibitor. Fig 6a indicates that the surface of the MS is smooth. Fig 6b shows the image of the MS sample immersed in 0.5 m acetic acid for 24 hours. It is noted that the surface of the MS was rigorously corroded because of the aggressive attack of 0.5 m acetic acid. Fig 6c shows the SEM image of the MS immersed in the acid solution in the presence of 15 mm hexamine for 24 hours. From the comparison of Fig 6a, b, c, and the results obtained above, it is clear that a protective film has been formed by the inhibitory molecules on the surface of the MS, which leads to a significant inhibition of the corrosion of MS in 0.5 m acetic acid. The 4 nitrogen atoms of hexamine having high electron density must have functioned as the reaction center. The inhibition action can be accounted by the interaction of lone pair of electrons at the nitrogen atom on the positively charged metal surface 44. The presence of 6 ethylene groups also helps to lead to enhanced electron density at the nitrogen atoms, which enhances its adsorption on the metal surface. This in turn lead to an increase i.e. macromolecular size and higher number of N atoms of hexamine 45 might have covered almost all active site of MS. Hence the mechanism of the inhibitive action is probably due to the blocking of anodic and cathodic sides by adsorption, which enables the formation of protective insoluble film. Acknowledgement. The authors are thankful to the Department of Chemistry, Navy Science College, Surat for providing laboratory facilities.